Good morning, everybody. Today, meet the NEET program, ongoing program. Today, we have the discussion on chemistry. The topic is chemical kinetics. So, chemical kinetics, we are going to deal about the rate law expression. Rate law expression is nothing but concentration dependent reaction rate. Generally, if you do the reaction, say for example, a hypothetical reaction, I am taking a and B, and it's going to react, say it gives a product AB. This is a hypothetical reaction. In this case, generally, when the concentration of the reactant is high, the rate of the reaction is also high. So that rate is always directly proportional to the concentration of the reactants. This is generally we got to use this kind of expression for rate law expression. And also rate law expression means we are bringing the rate constant so that it has to be converted into the equal rate is equal to, you have to put one constant, and that is called a reaction constant, rate of the reaction, rate constant for the reaction. So in this case, then the concentration A and B is, say for example, as 0. This is called, we can call it as the power is always called the order. In this case, rate will become rate constant when the order of the reaction is 0 order reaction. So that A power 0, 1. So 1 into 1, then the rate is equal to K. So K is also, we can call it as a specific reaction rates. This is a rate constant, but still a specific reaction rates. So within this introduction, we are going to deal about the rate constant and the order of the reaction and one more, molecularity of the reaction. So okay, yes, okay, second slide. So now we can see that rate is K into, say for example, concentration A, and K we can rearrange. Rate constant will become rate divided by concentration, general reaction. And also we should know that the rate constant unit and the rate of the reaction unit. Generally, the rate unit is actually a decrease in concentration divided by time. So concentration divided by time. So generally, the concentration always expressed in moles per liter, molarity, or moles per liter, and this time in terms of second it goes up. So moles per liter per second rate. So, and of course rate unit is always constant. This is the one, but depends upon the order of the reaction. The constant rate constant unit will be varying. See, for example, we have to know the basic difference between order and the molecularity of the reaction. Let us say I will be giving the A plus B will reacting, you will get a C plus D. Whereas this is a small C and D, and here A and B. This is a and B. These are all stoichiometric. After the balance reaction, we have to call it as a stoichiometric coefficient. But in the same reaction, if you wanted to know the order of the reaction, rate is equal to constant case and the concentration of A and the concentration of B, but we have to put say for example X and Y. Whereas here A plus B, A and B, these are all molecularity. We will call it as molecularity. It will be determined by balance in the elementary reactions. Whereas X and Y, this is we have to call it as order of the reaction. Order. Basically, the difference between molecularity and order of the reaction The order can be calculated always by experimentally. This is most important. Whereas this is a molecularity, just by balance the reaction, you will get the stoichiometric coefficient, that is the molecularity. Of course, we got to use a stoichiometric, element reaction only, the stoichiometric coefficient is equal to molecularity, but not complex reaction. Complex reaction, there is no meaning of molecularity. So within this introduction, we will say some of the examples. See, for example, first order reaction. Basically, the molecularity is always like a 1, 2, 3, etc. Just whole number, but order is maybe 0 or 1 or 2 or even minus 1.2, 3 by 2, something like a fractional also it is possible. But the fractions is not possible for molecularity. Always balance the reaction. Basically, this is of course a different experimentally. The basic difference we should understand. That's it. And in terms of the this is all cases molecularity and order. This is only for element reaction. We got to talk about this one. And one more type of reaction, that is called a complex reaction. For complex reaction, there is no meaning of molecularity. So, however, in the complex reaction means the reaction goes more than one steps. So that in the several within the intermediate steps, there is a one step is a very, very slowest step. That is a slowest step is a rate determining steps. Slowest step is a rate determining step. Like this we have called this. So in this slowest step only, molecularity and order both should be same. Molecularity and order both should be same. That is for the rate determining steps only, we have to count it. This is a basic difference between element reaction and complex reaction. So let us see some of the examples of the reactions in terms of order. See, for example, this is a one case first order reaction, decomposition of first order reaction. Decomposition of N2O5, that is nitrogen pentoxide. Nitrogen pentoxide N2O5 gaseous state decomposed into NO2 and of O2. So you can put it to in. This is of course in this case the rates is equal to K into N2O5. In fact, if we wanted to balance the reaction, maybe generally to balance the reaction it is supposed to be not a fraction. We got to multiply by 2 so that it should be 2N2O5 and this should be the 4 and this should be the 1. But it seems to be 2N2O5. This is a order of the reaction is 1, but molecularity of the reaction is 2. So, but this is first order reaction. Second examples, if you take an examples, H2 combination reaction of H2 gas plus iodine gas. This is a 1. You are going to get 2HI. In this case, order of the reaction is 2. So rate is equal to K into H2 I2, concentration of both. Of course, the order of the reaction is 1 with respect to hydrogen. The order of the reaction is 1 with respect to iodine. So that 1 plus 1 equal to 2. Order is 2 for this reaction. And simultaneously, if I say a decomposition of the same reverse reaction, 2HI undergoes decomposition, it giving back H2 plus I2. In this case, we have the molecular is 2, but actually it is a zero order reaction. Zero order reaction, so that a rate will become K and HI will become 0. Concentration remains constant. That is why we got to say about the order of the reaction, especially zero order reactions. And let us say one more example of this is a maybe we can see order of the reaction is 1, but this is a bimolecular reaction. Molecular is 2, the bimolecular reaction. This is also bimolecular reaction, decomposition of 2HI, bimolecular reaction, but zero order reaction. This is the way we need to understand the difference between both. And of course, one examples that is a third order reaction. Third order reaction, NO plus what nitric oxide undergoes oxidation in the presence of oxidation, and it gives a 2NO2. This is one of the important key steps manufacture of nitric acid, nitric oxide is used. So in this case, we have to use 2NO2. This is a trimolecular reaction. Of course, this trimolecular reaction came from the balance of the chemical reaction, and the order of the reaction is also 3. So this rate will become K is equal to NO power 2. The rise to the power always describes order. Whereas this is O2 concentration. So that this 1, so 2 plus 1, this is also order of the reaction is 2. And maybe we can have the one more reaction is a fractional order. So fractional order means, of course, this is a balanced reaction only. A decomposition of acetaldehyde, CH3, CHO. This will be undergoes a thermal decomposition. It's giving actually a methane and a carbon monoxide. Both are in gaseous state. This is a fractional order. It was found that the rate is 1.5. That is a 3/2 CH3 CHO. 3/2. So always the order of the reaction always can be experimentally verified, experimentally determined, whereas the molecularity of the reaction always determined by balance in the element reaction. That's the basic difference between these two. And one more last, we should understand the rate constant unit because it varies, depends upon the order of the reaction. That also we can have the some examples. See, for example, the basic fundamental rate law expression, rate is equal to K into A power something constant is there. See, for example, what is a rate constant unit? K unit for zero order reaction. So again, the same reaction, I mean the rate law expression we got to rearrange, and finally you are going to get a rate divided by concentration. If it is a zero order reaction, we can put it E power 0. The unit for rate is actually concentration divided by time, and this will become A power 0. Of course, A power 0 is equal to 1. I mean, this is a moles per liter per second. For the zero order reaction, unit for rate terms both are same. Now, have one more example of first order reaction. The first order reaction rate is equal to K into A power 1, so that K is equal to rate divided by concentration. I mean that is 1. So this one, what you are going to get moles per liter divided by second, that is a time, and this also concentration, the denominator, this is also moles per liter. This moles per liter going to cancel, and finally second will goes up and it will become second inverse. So if you note it down the rate constant unit for any numeric problem, you will get to know that without telling the what is the order of the reaction. By looking the unit of rate constant, you can get conclusion that this is a first order reaction. So generally, for a general equation, we can arrive to determine the rate constant. See, for example, rate will become k into a power for nth order reaction. So without going for more details, even you can have the very tricky idea to calculate the order of the rate constant, unit for rate constant for any order of the reaction. So your rate divided by concentration n, and this will become rate will become moles per liter divided by second, and this will become concentration. Of course, this is n, this also concentration n. This is a 1. So this is a concentration, this is a concentration, and 1 it goes up, then 1 minus n. So that concentration 1 minus n into second inverse. This is a general unit for rate constant. So that concentration will become moles per liter 1 minus n and the second inverse. This is the way we can get conclusion. So thank you very much, students. Probably next Meet the NEET we will have some other topic, interesting topic. Thank you very much. Bye.